Let me begin with a small, almost ridiculous image. A university cafeteria, students talking, plates clattering. In the middle of that ordinary noise, a young physicist named Richard Feynman is not thinking about the deepest equations of the universe. He is watching a plate spin in the air. Someone tosses it. The plate rotates smoothly, but it doesn't just spin like a coin on a table. It wobbles. The center stays roughly in place, yet the rim tilts and circles as it spins. Two motions are happening at once. There is the fast rotation of the plate around its center, and there is the slower turning of the tilt itself, the wobble, what physicists call precession. Most people would see a plate and see nothing more than a plate. Feynman saw a puzzle. He noticed something peculiar. The wobbling motion didn't occur at the same rate as the spin. It was related but not identical. If you look carefully, the wobble seemed to occur at a frequency that was twice the rate of the visible rotation marking on the plate. That is already strange. Why twice? Why not the same? Why not some messy fraction? Now, this is not mystical. It is classical mechanics, the physics of rotating bodies. When an object spins in 3 dimensions, especially if it is not perfectly aligned with its axis of symmetry, its motion becomes richer than our everyday intuition suggests. The plate's mass is distributed in a flat disk. When it tilts, gravity and angular momentum interact in a precise geometric way. The equations describing rigid body rotation predict a specific relationship between spin and precession. But here is the important part. Feynman did not approach it as a heavy, formal calculation. He played with it. He imagined it. He treated it as a toy problem. Within minutes, he derived the relation between the 2 frequencies. It was clean, elegant, satisfying. What makes this story powerful is not that the math was impossible. Any trained physicist could eventually work it out. What matters is the attitude. Feynman saw something ordinary and refused to treat it as trivial. He trusted that even a wobbling cafeteria plate could contain a doorway into deeper structure. When you analyze a spinning plate, you are forced to confront how rotation really works. Not the simple rotation of a door on hinges, but rotation in 3-dimensional space. There are axes. There are conserved quantities. There is angular momentum, which does not behave like linear momentum. It resists change in direction. It couples different motions together. In daily life, rotation feels simple. You turn a knob. You spin a wheel. But the mathematics behind rotation is subtle. It involves geometry at a deep level. Angles combine in non-intuitive ways. Directions matter. The order of rotations matters. If you rotate an object around one axis and then another, you do not generally end up in the same orientation as if you reverse the order. This small observation, that rotation in 3 dimensions as hidden structure, is what made the spinning plate more than a cafeteria curiosity. It was a reminder that even the simplest motions contain layers of pattern. Feynman later said that playing with that plate helped revive his love for physics during a period when he felt burned out. But more importantly, it trained his attention. It tuned his mind to symmetry, to frequency relationships, to geometric consistency. And here is the quiet irony. The mathematics of rotation that describes a wobbling plate in a cafeteria is deeply connected to the mathematics that describes the spin of an electron, something we cannot see, cannot touch, and cannot picture in any ordinary way. The plate is visible. The electron is not. The plate obeys classical mechanics. The electron obeys quantum mechanics. Yet both are governed by the geometry of rotation in space. The plate was simple. The implications were not. Now let's leave the cafeteria and move into the microscopic world. When physicists say an electron has spin, it is very tempting to imagine a tiny ball physically rotating, like a miniature planet spinning on its axis. That picture is natural. It feels comfortable, but it is also wrong. An electron is not a little solid sphere with a surface that can spin in space. As far as we can measure, it behaves like a point particle. It has no known size in the classical sense, and yet it possesses angular momentum. It has spin. This is already a warning that our intuition is going to fail us. In classical physics, spin is literal rotation. A spinning basketball has angular momentum because its mass is distributed in space and physically rotating. You can see it. You can touch it. You can slow it down with friction. But an electron spin does not come from little pieces of matter circling around inside it. If it were physically spinning like a tiny charged sphere, calculations show the surface would have to move faster than the speed of light to produce the observed angular momentum. That is impossible according to relativity. So when we say spin, we mean something more abstract. It is an intrinsic property. It behaves mathematically like angular momentum, but it is not caused by classical rotation. Now here is where things become deeply strange. If you take a classical object and rotate it 360 degrees, one full turn, it returns to the same orientation. There is no ambiguity. A full circle brings you back to where you started. But for particles like electrons, which are called spin particles, something unusual happens in the mathematics. If you rotate the quantum state of an electron by 360 degrees, it does not return to exactly the same state. Instead, its wave function changes sign. That might sound harmless, just a minus sign. But in quantum mechanics, the wave function encodes all measurable information about the system. Changing its sign is not like repainting a car. It affects how it interferes with other quantum states. Only after rotating the electron 720 degrees, 2 full turns, does its quantum state return completely to its original form. Pause and consider that carefully. In our everyday world, 2 full rotations are redundant. After the first full turn, you are already back. The second does nothing new. In the quantum world, the first 360 degrees is incomplete. The universe keeps track. Only after 720 degrees is the system fully restored. This is not speculation. It has been confirmed experimentally in neutron interference experiments. When beams of particles are split and recombined, the phase differences created by 360-degree rotations produce measurable interference patterns. The mathematics is precise. The predictions match observation. But here is the tension: we can calculate it perfectly, yet we cannot explain it in familiar mechanical terms. What exactly is rotating inside the electron? Nothing in the classical sense. What is physically different after 360 degrees? The answer lies in the structure of the quantum state, something that lives in an abstract mathematical space, not ordinary three-dimensional space. The mathematics used to describe spin to particles involves objects called spinors. Spinors are not vectors like arrows pointing in space. They have deeper symmetry properties. Under rotation, they transform in a way that ordinary objects do not. And this transformation rule that 360 degrees introduces a sign change is built into the geometry of three-dimensional space itself when described through quantum mechanics. We can write the equations. We can apply them in technologies like MRI machines and quantum computers. We can measure the magnetic moment of the electron to extraordinary precision. Yet if someone asks, why does nature require 720 degrees for these particles? The honest answer is that we do not know. We know how it works. We do not know why reality is built this way. The spinning plate hinted that rotation has hidden structure. The electron proves that the hidden structure goes far deeper than intuition can reach. So let us slow down and separate carefully what we truly understand from what we merely calculate. Physics at its best is extremely precise. When it comes to the electron spin, we are not guessing. The theory that describes it, quantum electrodynamics, is one of the most accurate scientific frameworks ever constructed. It was developed in part by Richard Feynman, along with others, and its predictions have been tested to an astonishing number of decimal places. Take the magnetic moment of the electron. Because the electron has spin and electric charge, it behaves like a tiny magnet. The strength of that magnet can be calculated from theory. Experiments measure it independently. The agreement between theory and experiment is so precise that the numbers match to more than 10 decimal places. In science, that level of agreement is extraordinary. It is not vague. It is not approximate. It is exact in a way that borders on shocking. This tells us something important. The mathematical structure describing spin to particles is not an optional model. It reflects something real about how nature operates. We know that electrons have intrinsic angular momentum equal to 1/2 of a fundamental unit called their Planck's constant divided by 2 We know that when we measure the spin along any direction, we will always find one of 2 possible outcomes. We know that rotating the quantum state changes its phase in a precise, predictable way. We know how spin interacts with magnetic fields. We know how it combines when multiple particles are involved. We know the symmetry rules that govern it. All of this knowledge is operational. It allows us to build devices. It allows us to design experiments. It allows us to predict results before they happen. But notice what kind of knowledge this is. It is knowledge of relationships. If we rotate by this amount, the wave function transforms in that way. If we apply this magnetic field, The energy shifts by that amount. If two spins interact, they combine according to these algebraic rules. The theory gives us a network of consistent transformations. What it does not give us is a mechanical picture. In classical physics, understanding often meant visualization. You could imagine gears turning, planets orbiting, waves rippling through water. The mental image matched the equations. With quantum spin, the mental image collapses. There is no tiny spinning top inside the electron. There is no physical surface completing two turns. There is only a mathematical object, a state vector, living in an abstract space. When we rotate the electron, we are not twisting a material thing in ordinary space. We are transforming its state in a complex vector space that encodes probabilities. The fact that this abstract transformation corresponds to physical measurement outcomes is both beautiful and unsettling. We know how to calculate the transformation using matrices. We know that the relevant symmetry group for spin to particles is SU, which is closely related to the geometry of three-dimensional rotations. We know that ordinary spatial rotations form a group called SO, and that SU is a kind of double cover of it, which mathematically explains why 720 degrees are required instead of 360. But if you ask, why is the universe described by SU rather than something else? Physics does not answer. It describes the structure. It does not justify it. This is the boundary we keep reaching. We know the formalism. We know the experimental confirmation. We know the predictive power. But the deeper, why? Why these symmetries? Why this geometry? Why this mathematical elegance remains beyond explanation. And that difference between calculation and comprehension is not a small philosophical detail. It is the central tension in modern physics. We have learned how the pattern behaves. We have not learned why the pattern exists. To make this less abstract, let's try to build an image, not because the image will be perfect, but because it may gently stretch intuition in the right direction. Imagine you are holding a coffee mug in your right hand. Keep your elbow close to your body. Now rotate your wrist clockwise one full turn, 360 degrees, without letting go of the mug. Your arm becomes twisted. Your wrist feels strained. You cannot easily return to your original comfortable position without rotating backward. Now continue turning your wrist in the same direction another full 360 degrees. You have now completed 720 degrees of rotation. Strangely, with a bit of movement in your shoulder and elbow, you can untangle your arm and return to your starting position without ever reversing the direction of rotation. This demonstration is sometimes called the belt trick or Dirac string trick. It shows that in three-dimensional space, there are rotations that look complete after 360 degrees, but are not topologically equivalent to doing nothing. Only after 720 degrees can certain twists be smoothly undone. What is happening here is not magic, it is geometry. The configuration of your arm is not determined only by the orientation of your hand. It includes how the rest of your arm is arranged in space. After one full turn, the hand is back in its original direction, but the twist in the system has not disappeared. After two full turns, the twist can be continuously deformed away. This physical trick is only an analogy, but it hints at something real. Rotation in three dimensions has deeper structure than a simple circle. In mathematics, rotations in ordinary space are described by a group called SO. But when physicists describe quantum particles like electrons, they use a related but slightly different structure called SU. SU has the peculiar property that it requires 720 degrees of rotation to return a spinor to its exact original state. You can think of SU as wrapping around SO twice. For every ordinary rotation in space, there are two distinct quantum states that correspond to it. After 360 degrees, you move from one to the other. After 720 degrees, you come back fully. This is not something we invented to be clever. It is forced on us by experiment. The interference patterns observed in spin experiments match the SU transformation rules precisely. But here is the difficult part. The coffee mug trick still involves tangible objects. Your arm is made of atoms. The twist is physical. You can feel it. An electron does not have an arm. It does not have a visible structure that twists in space. The rotation of an electron is a transformation of its quantum state, not a mechanical twisting of matter. The belt trick gives us a shadow of the geometry, but it does not explain why reality, at the most fundamental level, follows that geometry. Why should the universe care about these abstract group properties? Why should the mathematical requirement of a double cover have physical consequences? We can say that spinned-up particles are described by spinors, and spinors transform under SU. We can say that SU is the double cover of SO, which explains the 720-degree property. Each of these statements is mathematically consistent and experimentally verified, yet none of them answer the deeper questions. Why is physical reality built on this structure rather than another? We are describing the scaffolding of the universe using group theory, and the scaffolding matches observation perfectly. But the reason that this scaffolding exists at all remains unexplained. The analogy with the coffee mug helps us see that 360 degrees is not always as simple as it appears. The mathematics shows us that rotation is richer than intuition suggests, and quantum mechanics forces us to accept that this richness is not just a mathematical curiosity, it is woven into the behavior of matter itself. The world, at its core, seems to care about geometry more than our instincts do. At this point, the real difficulty is not mathematical. It is psychological. Human intuition was not designed to understand quantum spin. It was shaped by evolution to survive in a world of falling rocks, moving animals, and solid surfaces. Our brains compress reality into manageable patterns. We see continuity where there is discreteness. We see solidity where there is mostly empty space. We expect rotations to behave like doors on hinges. When something violates those expectations, we feel confusion. Not because the universe is being irrational, but because our mental tools are limited. Consider how we normally understand motion. If you push a ball, it rolls. If you spin a wheel, it turns smoothly. If you rotate a book 360 degrees, it is back where it started. These are reliable experiences repeated thousands of times throughout life. They form deep neural habits. Quantum mechanics does not respect those habits. When physicists say an electron rotated 360 degrees changes sign, the immediate reaction is to search for a hidden mechanism. We imagine some tiny internal gear or structure completing only half a rotation. But that is our classical bias, trying to force an image onto something that may not have one. The quantum state of a particle is not a picture in space. It is a vector in a complex mathematical space called Hilbert space. The rotation occurs in that abstract space. We project the results of that rotation into measurable quantities like magnetic orientations. But the transformation itself is not a physical twisting you could film with a camera. This gap between mathematical description and visual imagination is where most discomfort arises. In classical physics, explanation often meant reduction to familiar mechanisms. Heat became molecular motion. Sound became pressure waves. Light became electromagnetic waves. Each step replaced mystery with imagery. Quantum spin resists that kind of reduction. There is no deeper mechanical layer underneath spin that restores everyday intuition, at least none we currently know. Instead, we are left with symmetry principles. Symmetry in physics is not decorative, it is structural. The conservation of energy comes from symmetry in time. The conservation of momentum comes from symmetry in space. These are not poetic statements, they are precise mathematical relationships proven through Noether's theorems. Spin arises from symmetry as well, specifically from the way the laws of physics remain consistent under rotations. When you require that the equations of quantum mechanics respect rotational symmetry, certain representations naturally appear. Among them are spin-to representations. In other words, once you demand that the universe behave consistently under rotations, particles like electrons almost inevitably emerge within the mathematical framework. But this does not dissolve the strangeness. It relocates it. Instead of asking, why does the electron behave this way? We now ask, why does reality obey these symmetry requirements at all? Our minds struggle because we want explanations to terminate in something concrete. A gear, a field, a mechanism. Symmetry feels abstract. It feels like a rule, not a thing. Yet increasingly, modern physics suggests that rules may be more fundamental than things. The electron spin is not a tiny spinning object hidden somewhere in space. It is a manifestation of how quantum states transform under rotations. It is a reflection of the geometric structure of reality itself. The difficulty is not that the mathematics is wrong. It is that our brains evolved for survival, not for group theory. We expect the universe to resemble our experience. Instead, our experience appears to be a simplified surface layer of a far deeper, more abstract order. And confronting that gap between intuition and structure is where the real intellectual challenge lies. Now we arrive at a more uncomfortable place, the boundary of knowledge. Up to this point, everything we have discussed is solid science. The mathematics of spin particles works. The experiments confirm it. The technologies built from it function reliably. There is no crisis in prediction. The uncertainty lies somewhere else. We do not know why the universe is quantum in the first place. That may sound like an odd statement. Quantum mechanics is our most successful physical theory. It explains atoms, chemistry, semiconductors, nuclear reactions, lasers, and the stability of matter. Without it, the modern world would not exist. But the question is not whether it works. The question is why it works that way. Why is reality described by wave functions instead of definite trajectories? Why are probabilities fundamental rather than temporary expressions of ignorance? Why do particles possess intrinsic spin at all? When physicists write down the equations of quantum mechanics, certain features are simply built into the structure. States are vectors in Hilbert space. Observables are operators. Measurements produce discrete outcomes. Rotational symmetry is represented through mathematical groups like SU. We accept these ingredients because they match experiment. But we do not derive them from something deeper. For example, consider spin itself. Spin to particles exist. That is a fact of observation. But nothing in classical physics demands that such particles must exist. There is no everyday principle that predicts a 720-degree restoration rule. The standard model of particle physics classifies particles by properties such as mass, charge, and spin. It organizes them beautifully. Electrons, quarks, neutrinos, photons have spin 1. The Higgs boson has spin 0. The structure is consistent. It is mathematically elegant. It allows extremely accurate predictions. But it does not answer why these particular values appear. Why spin D and not spin N? Why 3 generations of particles? Why these specific symmetry groups and not others? Physicists can propose deeper theories, grand unified models, string theory, extensions of symmetry, but so far, none have experimentally replaced the current framework. Even more puzzling is the fact that spin is tied to the fabric of space-time itself. In relativistic quantum theory, particles are classified by how they transform under the symmetry group of space-time, known as the Poincare group. Spin is not an add-on. It is embedded in how matter fits into space-time structure. This suggests something profound. The properties of particles may arise from the geometry of the universe itself. But again, this moves the mystery rather than eliminating it. Why does space-time have this geometry? Why does it admit these representations? Why is the mathematical structure of the universe so tightly constrained? When we press further, physics becomes quieter. There are ideas, there are hypotheses, there are attempts at deeper unification, but none yet provide a final explanatory layer beneath quantum theory. We are left with a pattern that works flawlessly and yet feels ungrounded. It is like discovering that a vast cathedral stands before us, perfectly symmetrical, internally consistent, breathtaking in precision, and realizing that we have no idea why this particular architecture exists instead of another. We can measure every stone. We can calculate every angle. We can predict how sound echoes inside. But we cannot explain why this structure, with these exact symmetries, is the one reality chose. That is not ignorance in the ordinary sense. It is the recognition that explanation may have layers, and we may not yet have reached the bottom. Spin-deep particles are not mysterious because we cannot compute them. They are mysterious because we do not know why the universe requires them at all. And that distinction changes how we think about knowledge itself. The spinning plate was simple. It was something anyone could see, touch, and toss in the air. Yet even that small observation contains a lesson about the subtlety of physical reality. When Feynman worked out the wobble mathematically, he was not uncovering some hidden property of matter. He was discovering a relationship between motions, a structure embedded in the geometry of rotation. That simple relationship foreshadows the deeper structure that governs quantum systems. Quantum mechanics, by contrast, operates in a realm we cannot directly perceive. Electrons do not spin like tiny planets. They are not composed of matter that we can visualize. Their spin is a property of an abstract state, a vector in a multidimensional mathematical space. This vector describes probabilities and potentialities. Rotating it changes the probabilities in precise ways. We can calculate these changes, predict measurement outcomes, and even manipulate them in experiments. Yet, no physical image can make the behavior intuitively obvious. The double rotation of spin particles illustrates the peculiar nature of quantum reality. While a classical object returns to its original orientation after one turn, the wave function of an electron requires 2 full rotations to return to its original state. This is not a limitation of our measurement. It is a fundamental feature of how matter is structured. The double covering property of SU, the mathematical framework describing spinors, ensures this. Experiments confirm the prediction repeatedly, and technology exploits it. Quantum computers, MRI machines, and particle accelerators all rely on the precise manipulation of spin and its associated properties. Even so, the origin of these structures remains mysterious. Physics tells us what happens. It gives exact rules and equations. It allows us to design experiments, predict results, and understand interactions with astonishing accuracy. But physics does not explain why these rules exist. Why does the universe enforce these symmetries? Why does it require spin rather than some other fractional spin? Why is the mathematical framework so effective in describing reality? The equations work. They match experiment. They provide predictive power. But the deeper why is silent. The spinning plate, the electron, and the abstract mathematical spaces are all manifestations of the same principle. The universe is governed by patterns. These patterns are often hidden, subtle, and counterintuitive. In classical mechanics, patterns are visible and tangible. In quantum mechanics, patterns are abstract and mathematical, yet no less real. Feynman's insight was to recognize that even playful observations could reveal fundamental structures. The plate was a toy, but it contained the seeds of understanding far beyond its simple motions. Humans struggle to understand this because intuition evolved to handle macroscopic objects, not abstract symmetries. Everyday experience misleads us. We expect rotation to behave one way, solidity to be obvious, and motion to be continuous. Quantum reality defies these expectations. Spin particles remind us that intuition is limited. Calculations are reliable. Mental pictures are often misleading. The universe operates according to rules that are not bound by our perception or imagination. By studying these hidden structures, we uncover a profound lesson. Reality is not simply what we see. It is a network of relationships, a fabric woven from symmetries and mathematical consistencies. What seems strange or impossible is often a reflection of the deep order underlying the universe. The spinning plate was simple. The electron's spin is complex. But both are manifestations of the same truth. The world is organized around patterns, not objects, and the deepest layers of these patterns remain mysterious. Feynman's playful curiosity shows that discovery begins with attention to small, observable phenomena, yet leads to insights about the fundamental structure of the universe. The boundary between classical intuition and quantum abstraction is not a failure. It is an invitation to explore, to calculate, and to reflect on the surprising depth of reality. The universe is both knowable and enigmatic, and in understanding that tension, we glimpse a more profound perspective on the nature of existence itself. When we consider the behavior of spin D particles, it becomes clear that much of the strangeness arises from the way humans think about the world. Our brains evolved to deal with objects that are large, tangible, and predictable. We navigate forests, throw stones, track moving animals, and handle tools. These are all tasks rooted in classical physics, where forces, trajectories, and rotations behave in intuitive ways. Our mental models assume that motion is continuous, rotations restore objects after 360 degrees, and matter is solid and distinct. Quantum mechanics violates many of these intuitive assumptions. The state of an electron is not something we can visualize. It is a vector in a complex, multidimensional space. When we talk about rotating an electron, we do not mean spinning a physical object. We mean transforming its state vector according to the rules of quantum mechanics. These transformations are exact, predictable, and measurable. Yet they do not correspond to anything in everyday experience. This gap between calculation and intuition creates discomfort. We naturally search for causes, mechanisms, and images that match our mental expectations. We want to see a tiny sphere spinning or a gear turning. But nature is not obligated to satisfy our desire for intuitive pictures. Spin is an intrinsic property. It is defined by how the state transforms, not by any physical rotation in three-dimensional space. The mathematics describes what is measurable. It does not provide a mechanical explanation because no such explanation exists in the classical sense. We can, however, gain some insight through analogy and geometry. Rotations in three-dimensional space are more subtle than they appear. The order of rotations matters. Combining rotations around different axes does not commute. This non-commutativity underlies the counterintuitive behavior of spin-T particles. Analogies such as the belt trick or twisting a mug with your arm show that 360 degrees is not always sufficient to restore a system to its initial configuration. 2 full rotations are required. In classical objects, these constraints are hidden or trivial. In quantum systems, they are fundamental and measurable. Symmetry lies at the heart of these phenomena. Physical laws remain unchanged under certain transformations, such as rotations in space. Noether's theorem links these symmetries to conserved quantities. Spin arises naturally from the requirement that the laws of physics respect rotational symmetry. Particles like electrons are spin-T because the mathematical structure describing rotations in 3-dimensional space requires such representations. SU, the relevant symmetry group, is a double cover of SO, which explains why 2 full rotations restore the quantum state. Even with these explanations, the deeper why remains unresolved. Why does the universe obey these symmetry principles? Why does reality admit SU as the fundamental group describing spin? Why does nature favor spin the particles instead of some other configuration? Physics provides a map, a set of rules that match experiment, but it does not answer why these rules exist rather than others. This boundary between understanding how things behave and understanding why the framework exists is one of the most profound challenges in science. Humans struggle with this because our intuition is limited. We evolved to understand objects, not abstract symmetries. Quantum mechanics forces us to accept that some aspects of reality cannot be visualized in the classical sense. We must rely on mathematics as a tool to describe and predict behavior, even when mental imagery fails. Accepting this requires humility and openness to the unexpected. Spin particles are a clear example of this challenge. They obey precise, measurable rules, yet defy mechanical intuition. The universe is structured not for human perception, but for consistency, symmetry, and mathematical coherence. Recognizing this allows us to see beyond familiar appearances and appreciate the subtle, abstract order underlying reality. The world is governed by relationships, transformations, and patterns that often escape direct visualization, yet these patterns form the foundation of everything we measure, manipulate, and observe. The story begins with a spinning plate tossed casually in a cafeteria. Its wobble, subtle yet precise, revealed relationships in rotation that most people would ignore. Feynman noticed patterns that connected angular momentum, geometry, and motion. What seems simple and ordinary on the surface turns out to hint at far deeper structures. That plate, moving under the laws of classical mechanics, is governed by rules that can be calculated, measured, and understood. Its wobble can be described mathematically with a few lines of derivation. Yet even this simple system contains a lesson. Rotation is more subtle than intuition suggests, and patterns govern motion in ways we do not always perceive. When we move from plates to electrons, the lessons become profound. Electrons are not little spinning spheres. Their spin is an intrinsic property, a quantum number that cannot be visualized directly. Yet, like the spinning plate, the electron exhibits patterns that can be measured and predicted. Its spin transforms according to precise mathematical rules under rotations. Rotate it 360 degrees and its quantum state changes sign. Rotate it 720 degrees and it returns to its original state. This is not speculative. It is confirmed through interference experiments with neutrons and other spin-E particles. Calculations match observation with astonishing precision, yet we cannot picture a tangible mechanism. The behavior exists in an abstract mathematical space. The mathematical structures used to describe spin reveal a deep and subtle order. SU symmetry governs spin particles. It is a double cover of the ordinary rotation group SO, which explains the requirement for 2 full rotations. This symmetry is not arbitrary. It is forced by the need for consistency in the quantum formalism. The double rotation property appears in experiments exactly as predicted, yet the reason that nature chose this framework rather than another remains unknown. We know how spin behaves, how it transforms, and how it interacts with fields and other particles, but the deeper why eludes us. This gap between calculation and understanding illuminates a profound truth. Physics excels at describing patterns. It predicts with stunning accuracy. It allows us to manipulate and exploit quantum systems. Technologies from MRI machines to quantum computers rely on these principles. Yet the question of why the universe is structured in this way, the reason that patterns exist at all, is outside the reach of current explanation. Symmetry is fundamental, but why symmetry rules the universe is a mystery. The map works, but the origin of the map is unknown. Feynman's playful curiosity illustrates how attention to small, observable phenomena can lead to insights about fundamental structures. The spinning plate was trivial in one sense, yet it prepared the mind to recognize patterns and relationships that underpin quantum mechanics. The electron, invisible and abstract, obeys similar geometric and mathematical principles. Both demonstrate that the universe is governed not by objects alone, but by relationships, transformations, and symmetry. The patterns of motion, whether visible in a wobbling plate or encoded in a spinor, are the same language, expressed at different scales and with different consequences. The world appears strange because our minds are adapted to macroscopic intuition. We expect rotation to behave in certain ways, matter to be solid, motion to be continuous. Quantum reality violates these expectations. Calculations remain reliable, yet images fail. The spinning plate hints at the hidden order, and the electron reveals the full depth of abstraction. Reality is not simply made of things. It is made of relationships, patterns, and mathematical structure. The universe is deeper than perception, yet accessible through careful observation, curiosity, and reasoning. The simple plate, the abstract electron, and the patterns they reveal together suggest a profound philosophical insight. The universe is intelligible not because it resembles our intuition, but because it is organized by relationships and symmetries that can be discovered, explored, and understood, even if never fully visualized.